And when you go for when you go shopping online, you would see that there are a lot of recommendations about the products which actually you feel like buying. Okay, and that again has been uh, identified after processing a lot of your information using your personal computers cookies which are in your AI, which are in your browser pages. So based on that information or your earlier visits to the website, they decide that what exactly would you go for shopping. So that are prompted on your screen, flashes or flash screens come on your browser telling you that there are some discounts or some good products for you. So they recommend certain goods for you and products, which actually then gets converted into sales. So again, AI helps in improving the sales of those online suppliers. At the same time, the users get those products which they want. And that's again based on the okay, is this visible now? So we normally go for we have to think that what is the underlying platform going in. So sometimes we see that it can be the behavioral algorithms, or sometimes suggestive search when you do Google, or it's the predictive capabilities that define an AI system. Okay. So here again, when you say behavioral systems, the system behaves in a different way when you respond to it. And when you do a Google, lot of suggestions come to you before you actually there. You may have a keyword in your mind, but a lot of suggestions are come up. Again, it's based on a lot of data processing, and sometimes uh, we see the trend. Say, for example, weather forecasting is there, and you are told that tomorrow is this is going to be the weather. It's again a predictive capability of the system, of an AI system, using the previous data, using the wind velocity, and many other features of the climate, or based on the geographical maps, weather maps, and based on that, it makes certain predictions that what is the weather going to be for a particular week or a month. So, so we I'll actually kind of have to think that whether it's a behavioral algorithm which makes a system behave in a particular way, or is it the suggestive search, or whether it's the predictive capabilities that have to come in an AI system. Okay, before we actually go deep into AI, we need to see that what is exactly intelligence and where from this intelligence come. The underlying the underlying main source for any intelligent system is data. And when you process data, it gets converted into information. And when you process information, it gets converted into knowledge. And when you process knowledge, it gets converted into intelligence. So it's indirectly processing of data into information, into knowledge, and finally into intelligence. So if you see the size of these triangles, it gets reduced as you move from data to intelligence. So the size, this triangle here represents the size. So the size of intelligence is very less, and for getting so much intelligence, you need a lot of data. So more the data, better will be the capabilities of an intelligent system. So you have to supply a lot of data for a system to be more intelligent. And the process of conversion of data from data to information to knowledge and finally to intelligence will increase the capabilities of that system. So there are two things: the quantity of data you need, that's too much. You need, if you more and more data means more and more intelligence, and but the capability with which you process this data into intelligence is also very complex. So the complexity of intelligence is very high, and size is small. Okay, so here what with this slide, what I want to tell you is that for any AI system to be more precise, you need more data. And one is you need a lot of data, another is you need better algorithms which can extract this intelligence, which is very small in that data. You have to extract it from that data, first converting it into information, from that information into knowledge, and from knowledge into intelligence. But sometimes you can directly give knowledge from experts and convert that knowledge into intelligence. That would be the easier task than actually converting data into intelligence. But we have all ways to do it. We can directly take data as input, convert it into intelligence. We can directly take knowledge from experts and convert it into intelligence. And for both these ways, we have different approaches. Okay, so what is AI? It's a branch of computer science and that tries to mimic human intelligence. So we want machines to work like humans do. Okay, and so the intelligence, which is normally a computational process, we try to do it with computations. Humans also do computations, but it is in the subconscious mind they do it. But machines do it purposely with specific algorithms which they follow. Okay, so AI in computer science, we define it as a branch of computer science, and its main objective is to mimic human intelligence. We try to work as good as humans do. So here we have to get this intelligent behavior through computations. We'll talk about this a little after we have a few more slides. It will be a little more clear. Okay, so in our home, we have already these machines. You have a washing machine, you have a deep freezer, and you have a fridge. And we say that are these machines, though they also do a specific function in our households. We wash clothes, we deep freeze our food, and we also use this refrigerator for cooling. But are even though they have a specific function, are they intelligent? No, we'll say because they cannot do certain things on their own. They cannot do how humans do. So for example, if we take a washing machine, uh, there are washing machines where you switch a knob, and it's the human who has to decide that what type of fabric your this clothes have, and based on that the machine actually does the number of revolutions and the speed with which that revolutions are done, and then it washes. But a AI machine would have been working in a different way. You would put a dirty jeans in a machine, it will scan the image of that jeans, see that it is dirty, and then automatically switch on its knobs, control the number of revolutions, put the amount of soap or detergent inside the machine. So if it is automatically done, then will we actually say that there's some amount of intelligence in the machine. Similarly, if you put food in the in this deep freezer, if it is meat, it should accordingly control the temperature. Or if it is vegetable, it should automatically scan what is inside and then control its temperature. We'll say that they are intelligent. Had it been an AI-based refrigerator, you would have the better AI system in a refrigerator would have been if you would store your medicines, and if it's an expired medicine, it should scan the label of that medicine, see that the expiry date has run, automatically call the nearest medical store and refill the medicine without even letting you know if it is a very critical care medicine. So this way, we could have said that these devices are intelligent devices. So intelligent means some work has to be done, some computation to be done. It has to take some data, it has to process that data and make a decision, and then that should be useful as humans do. Intelligence is basically, so an AI system is to be filled with intelligence, which is to be derived either from data or from knowledge. So one way I said we can get that from data. Another is we can get that directly from knowledge. So any system which is capable of acquiring and applying knowledge. When you say acquiring, it has to get that knowledge from the experts. So if we have a, say for example, we have a doctor and he has a lot of knowledge about diseases, he knows what are the symptoms and what symptoms match a specific disease, and then he prescribes some medicines. So what he does is he has acquired a lot of knowledge during his education, and then when he sees the symptoms of the patient, he automatically he has certain rule base in his mind, and he identifies the disease. and based on those symptoms, and then using those symptoms and identification of disease, he then prescribes some medicine. So that is the application of that knowledge which he has actually acquired over the during his course of medicine. So that is how how that doctor became intelligent in a specific domain. So it is basically, you can also say that intelligence is basically a faculty of thought and reason. So you have to develop certain thoughts and then do some reasoning on that thoughts. Then only people can become intelligent. So a computation, what we think, what we acquire, if we think on that, that is the way humans become intelligent. And if we imbibe those qualities in machines, machines can become intelligent. So what are the features that humans use that when they which they are indicative or characteristics of knowledge of intelligence? So what are the so here we basically try to identify the key features of humans which make them intelligent, and they are that they store the concepts, real world concepts, abstractly. They use mathematics, hidden mathematics. They have a language to acquire those facts from the real world. They have problem solving skills. They have a lot of memory to store and then to retrieve from that memory. They have certain logical reasoning, and based on certain rules, they plan ahead. And one important thing that humans have is emotions, which we are still not able to put in machines. They do have morality and ability to learn. So that ability to learn makes systems dynamic. So a lot of research has been done in AI based systems which can imbibe this future called learning future in machines, because machines have to learn from data. And finally, it has to adapt to a specific environment. I hope this is clear up to now.
Yes, yes,
Now,
it's clear. And we proceed. Yes, Dr.
yeah.
Chachu,
Okay. So
continue.
the artificial intelligence basically studies how to achieve this intelligent behavior through computational means. This computer is basically computer has come from the word compute, and it only is meant for doing computations. And our objective is to extract this intelligence from data using computations. So it is basically, for computer science people, it is simply a computational process by which we extract intelligence from data and then use that intelligence in real world problems. So that is why we believe AI is a branch of computer science. There are certain questions, but we'll discuss those questions later. So why do we think that intelligence can be captured through computations? Okay, modeling processing that our brain does as a computation has to be proved to be successful. Hence, human intelligence can be argued be best modeled as a computational process. If you see that uh, today, the a very well-known researcher of artificial intelligence who has been working in this area for last 40 years says that basically it is neural networks which uses a common model for solving all type of problems. So he has come up with the conclusion after doing 40 years of research in AI, saying that it is basically the sort of human brain networks which are capable of solving problems. Okay, so later I will tell you what he actually means. He tries to say that computer science can solve any type of problem using a single model with a single algorithm. Okay. Earlier, what used to happen is if you wanted to see whether a machine is intelligent or not, what they will do is they'll put a computer in a room, and they will keep an interrogator in a separate room, and then they will ask the interrogator to ask questions from the machine. The interrogator would not know that whether it's a human inside the room or whether it's a machine inside the room. He will ask questions, and if the human interrogator could not reliably reliably decide whether the subject is a computer or a human, it will say that the machine test passed the Turing test. So it was given by a researcher called Turing. What did is he kept the machine in a room, and the interrogator started asking questions. So if the interrogator could not make out that whether it's a human or a machine, it would will say that computer passed the AI test. But today, even in our these websites, you will see that we have these CAPTCHA tests where you are given some jumbled text and you are asked to type it, just to see that whether it's a human or whether it's a machine, because machines cannot scan those jumbled text and then enter. So they don't want to overflow flow their machines with normally what used to happen is, if there would be a form, machines would fill the form on their own, which we normally used to know as bots. These software bots will fill the forms and then they will overpopulate the memory of a computer. So the computer will get hanged because of lot of data entry by the software. So the competitors normally would use this technique to make their competitors websites fail. So they will unnecessarily fill junk data in their web portals and in their databases, so that the database gets choked and the server would fail. So for this test has come, which is called CAPTCHA, where a human and an interrogator, where a human and the machine is classified. Here we see that if only this, normally humans can pass this test. Or sometimes even those images are shown and you are asked to identify a motor car or a bicycle or mountains in those images, just to see that it is human or it's a bot. So that's again a way of checking that whether this is an intelligent being or whether it's a bot or a software. Okay. So there's one definition about AI was given by Russell and Norvig, and they said that any system which can think and any system which can act, but if they can think and act rationally, then the system is an AI system. So this any AI system has to think and it has to act, but it has to act, but act rationally. Then it is an artificially intelligent system. So by now it is clear that the main ingredient of an AI system is knowledge. You have to extract that knowledge from data. But the problem with knowledge is that you have a lot of knowledge. You have to extract you'll have a lot of data and you have to extract a lot of knowledge. So knowledge is voluminous. So we have to have a system which can handle a lot of knowledge. And this knowledge again there's a problem in representing the knowledge. Okay, so we need to have a system where we can characterize that accurately. Also, the knowledge about the system is continuously changing. So it has to be dynamic. The representation has to be in such a way that it can act in a dynamic system. And it differs from data by being organized in a way that corresponds to the way it will be used. Knowledge normally is not is used by certain rules, and we call those rules as inference rules. These inference rules use that knowledge to make certain conclusions. So the representations has to differ from the data, how we normally represent data. So knowledge has to have a special type of representations, and those representations will be then used for making certain conclusions. A well-known AI-based system which has been used for a long is an expert system. And these AI-based systems which integrate knowledge from experts, and it's called a knowledge-based decision support system, or an intelligent decision support system. But some systems still need judgmental knowledge that resides in human experts. So such systems which use knowledge from experts is known as an expert system or a knowledge-based system. Or if it makes decisions, we call it as an intelligent decision support system. But this knowledge has to come from humans, because a lot of knowledge remains within the humans, which they have acquired or intuitively created from their experiences. In some decision situations, the support of data and models may not be sufficient, and additional support is needed, such as provided by the rule-based expert systems to substitute for human experts by supplying knowledge.
Daha ne yapıyor mu?
Here I will give an example.
Daha çok yapıyor mu?
In solving in solving very complex problems, what we do is we represent this knowledge in a specific representation, and then use predefined rules to extract more knowledge from them. Say, I'll give an example. So, for example, there's a standard rule that if A is father of B and B is father of C, then A and C are related, and the relation is the grandfather. A is grandfather of C. So, this can be now A B can be anybody. So if I say X is father of Y, Y is father of Z, you can easily say because of this rule that X is grandfather of Z. So now this rule can replace any fact. So if I say Sahil is father of Rahil, Rahil is father of Majid, you can easily say Sahil is grandfather of Majid. So based on this rule, we derive more information where we say that X is grandfather of Z. So such systems where we store the real world information in the knowledge base and use rules to extract more knowledge and decide. We say these are expert systems, and we expert system basically means AI based system because it is using knowledge of a particular domain. Okay, so we only need to know how to convert the real world knowledge which we normally can put as an expert in the natural language to a system, and how the system uses that natural language then to make inferences from that knowledge and decide in specific goals. Okay. Technologies that use qualitative knowledge rather than mathematical models to provide the needed support. So these knowledge-based systems, basically, they use the real-world facts. So for example, I'll give one more example. Say, for example, if in case of COVID, it is believed that if the temperature of a person is very high, he has cough, and so these two symptoms are if he is exhausted. So there's these are three basic let's assume three basic uh, symptoms which can tell us that that we should go in quarantine. So if the temperature of a person is high, if he has cough, and if he feels exhausted, we can say that he is probably having this. Is probably these are the symptoms of COVID. Now, this is the knowledge which we have got about COVID. The doctors know this. So if anybody come and we take his temperature, we see he's exhausted, we can simply say that he's infected. So this way, what happens is you are basically if you give this data to the machine and machine decides that whether he is having COVID or not. This is very simple way, but we fine tune it to a very large extent by seeing the history of many patients who had this type of problem, what type of temperature, what type of temperature range, and try to derive those rules from them, and then finally decide that whether he has a symptom of this or not. We say that the system actually is an AI based system. Okay, or we can say that it works on knowledge, so it's a knowledge based system. Okay, so what are the characteristics of artificial intelligence? The first of all, the knowledge is normally represented using symbolic representations. There are a lot of ways of representing this, so and a lot of languages which help you to represent. For those people who are not from computer science, they have tools where they give their knowledge in natural language in simple English sentences, and the system converts them into a symbolic representation. And this AI based systems, what they do is they do the processing of those symbolic representations of knowledge. So for example, somebody is expert in botany, he knows lots of things about a specific domain. Now what he does is he takes those domain knowledge in English sentences, gives it to a system, and the system converts it into a symbolic representation, which then goes for manipulation by the AI system. We'll talk that about later, and how we can make our own AI based system. So one thing which you need to remember is the main ingredient for any AI based expert or knowledge based system is you need to have knowledge, which we will technically call as knowledge base. Another thing which we need is an inference engine which can use this knowledge to make inferences so that we can give or extract more knowledge. Okay, so in case of and it uses non-algorithmic models for problem solving. So it is this this knowledge-based system. It's very simple to that if-then rule, where if you have this system, you have this disease. If you have this system and this system, then you have this disease, and then this is the solution or this is the prescription for that disease. So it's a non-algorithmic model of problem solving. Humans tend to be more non-algorithmic, but they depend more on rules which they have learned our experience, what we call as heuristics. So they use these heuristics or thumb rules, normally called, which they have learned our experience. And they may, these experience whenever they see any problem, they use that experience knowledge and solve that problem. So these heuristics are basically intuitive knowledge learned from experience. And by using heuristics, we do not have to rethink completely what to do every time we encounter a similar problem. So it automatically comes from the subconscious mind, which he has learned over the time. All methods use heuristics to reduce the complexity of problem. AI methods also use heuristics to reduce the complexity of problem solving. In very complex problems, you will see AI researchers and problem solvers use heuristics, which means these thumb rules, to actually optimize their searches or to optimize the mechanisms to solve those problems. As I earlier told you, we have to derive more knowledge from the already existing knowledge, which normally domain experts put in the knowledge base. The doctor has got a lot of knowledge. If you want to make an AI doctor, then you will have to take the knowledge from the doctor and store it in a knowledge base. But these systems do not stop there. They extract more knowledge from that knowledge which the doctor has. So they apply rules, and these rules are called inference rules. So these inference rules give capabilities that can build more knowledge from existing knowledge and heuristics, which they get from doctors or from humans. And this reasoning consists of inferencing from the facts. Facts are again from the knowledge facts. We say, for example, a doctor says if a temperature is more than this, 105, there is a chance that the patient has got malaria. So it's a general fact that a patient can have high temperature. And the rule says if he has got high temperature, it is chances are that he has a malaria. So the fact is the patient has a high temperature. So this fact and the rule helps us to basically build something called inference. So we can make an inference that this patient has malaria. And in addition to, doctors use these heuristics, which are thumb rules. So they say that if the sugar level of a patient is within, let's say, 100 and 102, it's a type 1 diabetic. So that is the rule they have. But if the patient has got somewhere around 121, we'll still call him as type 1. Or if he has got, let's say, near to 99, we'll still call them as type 1. So this is all heuristics, because humans have the flexibility of switching to here or there. They say that the machine, there's some small error in the machine, or that way they make certain heuristic approaches which help them to decide that what information they get from the machines, they can do certain alterations to them to actually identify the exact inference. Now, one more thing about which is the main characteristics of an AI system is to learn. These machines, these AI systems should have a capability to learn over time. And learning is again a sub area of AI. And this is very hot topic nowadays, that the capability with which a machines learn now is very, very high. It's going, it nearly everywhere you will see people doing research on machine learning. And this helps basically to machines to learn by changing their behavior or adjusting their behavior and reacting to the changes in the outside environment based upon the prior experiences. Or when we say prior experiences, or if we say that prior data. Okay, in computer science, when we say an experience or an example, it means a sample. Okay, so for example, if we have got in this class, if we have got around, let's say, around 100 participants, uh, by asking the height and the color and the length of the hair, we can move, we can probably detect the gender of the participant by just training the machine with the length of the hair, the foot size, the weight, the height of a person. We can detect the gender of the person who is of a gender of the participant. So that is we actually learned from the previous data that if the hair is short, if the foot size is more than 7, and if the height is more than 5.6, and if the weight is above 60, probably most probably he's a male. And if the length of hair is little more, and the foot size is small, the height is more than 5 and less than 6, and we cannot exactly detect the, but more chances are that we'll precisely detect the gender of that participant. So this is machines learn from the previous data and use that learning, whatever data, whatever information they have extracted, use that for making predictions in future. So we'll talk about the person whom we have not seen. We just seeing his data, we'll say what type of gender he has. Sometimes the same machine learning capabilities are used for detecting the emotions of a person, or for detecting the personality of a person, so that systems react in a different way. Okay, so this machine learning is basically learning from experiences. So in the learning from experiences and then using that for future. Is this clear up to now?
Yes, sir.
Yes, sir. Proceed, sir. Okay. So the learning capability of a system makes it more intelligent, because every time there will be new knowledge coming in, and the machines have to change their behavior based on the new knowledge. So these machines are normal, now we call them as artificially intelligent agents, sense the environment, they see what is the new data, and they react to that data, not only on the live data but on the historical data also. And so the one of the main property of an AI system is the capability to learn, and this is done with the machine learning, which is a sub area of of AI systems. As I earlier told you that knowledge comes from basically from data, and this data can be either labeled data or unlabeled data. So what happens is label data means to, if I have to predict that whether a participant is male or female, I need to first train my machine with some samples. Okay, I need to tell him that we have a participant who has a height of 6 feet, and he has a short hair, 2 inches of hair, and his foot size is 8. I have to give him, and he's a male. I have to tell him with around with 20 or more people that this is the data, and and we have to even tell them that whether they are male or female. And by training that also, it does not have to be biased data. That means we cannot tell only about males, we'll have to tell about females also. So we normally say that it is a balanced training data. So when we say label data, it means we need to give the input futures as well as tell the machine that whether it was a male or a female. Okay. And so uh, machine learning algorithms, what they do is they take this label data, they identify certain parameters in that data. So for example, when we say parameters, I'll just give an example. So for example, height sorry this length of the hair has more value than weight. Okay, females or males can be heavy. So it does, this future is not of that importance, but hair length will help us to predict a male or female very nicely. It will have more value than weight. Foot size again will have more value than weight, because females have smaller foot sizes. Maybe in extraordinary cases it may be large also. So But normally, when we talk of normal circumstances, then females do have a foot size of 5, 6, or 7, but males average foot size is 8 and above. 7 is also there. So foot size can be a more predictor in identifying whether it's a male or a female. So if I have a one which I have to distribute between foot size, hair size, height, and weight, I'll more probably give 0. 0.4 to hair size, 0.3 uh, to the foot size, and 0.2 to the height, and 0.1 to weight, because male and female can be weight, so it may not help me to predict it more nicely or more accurately. So the weights which were attaching to different features, actually based on the previous data, based on the earlier seen data, we will decide that what in the next unseen data, what should be the gender of that participant based on the earlier 20 examples, 20 participants data, which is labeled, about which I know that whether they are male and female, along with their test data. I can then use that to make predictions. So that when we, if you see this diagram here, we use labeled data, which is 20 samples, 20 examples from the participants about which I know the data as well as their male, female. And I give it to an algorithm. It identifies the parameters, the weights we should be given to different features, for example, in 0.4 to hair length. And then for prediction, unlabeled data, that means here there's a mistake, it has to be unlabeled data, because I need to see the gender of a participant about which only I get the data. I don't get the gender. My machine, my models detects whether it's a male or a female. Okay, so if we see what is machine learning, it's again a subfield of computer science that gives computers the ability to learn without being explicitly programmed. So you don't need to explicitly program the machine. The model learns the features from data, and based on the features, it decides on the unseen data. Okay, it predicts the unseen data. So there are there are many types of machine learning, but these are the main types of learning. One is supervised, where you need to give the data, and you need to give the label also. By training that, the machine identifies that what features are important and what are not. So supervised learning with a label training data set for so every machine in every learning algorithm, you need to give some training data, and then you need to test it with the test data. With training data, you need to give, if it's a supervised machine learning algorithm, then you need to give the features, input the features along with the output label. And if it's an unsupervised, you need to actually identify patterns in this unlabeled data. So there are some cases where you cannot label data. Say, I'll give an example. There's a well-known saying that birds of same feather flock together. Okay, so what it actually means is very similar data will always be scattered, will be clustered together. Okay, they will have features very similar. Say for example, if you see male people have very similar resembling features, females have resembling features, a very uncommon we use very few people, very few male and female features altogether, very that they're very few. And there may be very few outliers also, very some male which are very not male, which are very away from male, and females which are very away from female, again they will see very few. And that probably will be because of the corrupt data. So if you see machine learning techniques, they are classified either supervised, where you have input and output features, unsupervised, where you have data where you don't have the output, you have only the input data, and uh, you have then reinforcement learning, where you learn based on a reward. This reinforcement learning is more used in these robots, where if a robot does a work perfectly, we give him a reward. And if he does a mistake, say for example you must have seen that today these cleaning robots are freely available. It costs very few thousand rupees. Your room will get cleaned, and this robot, what it does is, it will clean the room, it will see the dust, it will go to that place, clean it, and come back to the charging port and start charging itself. So you don't need to be worried. As soon as some room is dirty, it will go, it will get activated, it will go, it will clean, and it will go back to its charging port. And it will not even collide with those walls, or it will not if it does by chance, then it will be punished for doing it, and next time it will take care in not clashing or in not colliding with objects in the room. So that's how what's meant by reinforcement. It learns to act based on the feedback, which is either reward. If it does a job perfectly, it gets a reward, it improves itself. And if it does a mistake, it is punished for it. So a punishment is done, and the machine automatically modifies its algorithm to next time take care that it does not collide. Okay, so there are three, this all these supervised, unsupervised, and reinforcement learning is classified as classification or a regression or clustering. Then when you say classification, say for example, if you have to classify a document based upon the subject, then probably if I take a botany paper, research paper, and I have to classify it and I have to suggest a good botany journal, I'll have to go through the contents and then see which is the relevant journal, and then cluster it with those botany research papers so that a research journal will come out. So that's clustering. So when you cluster data together based on certain features. Another is classification. Classification basically classifies objects based on properties. Say for example, you have this ham emails which come to your computer. They are from genuine senders, so they should be put in ham or inbox. And those mails which have some malicious content or which are from advertisement companies, then they should be put in the spam. So it classifies it whether it has to go in this or whether it has to go in this, it has to go ham or whether it is spam. Okay, so the that is classification. When you have to classify an object in one of the multiple classes. And then you have regression. Say for example, somebody wants to sell his house, and he wants a price for that house, he wants for how much he wants to sell it. So we need to give him a specific price of that house, an estimated price for which the house has to be sold. That comes under the regression. So the with the help of regression, he will get an some value for that house. Okay, so most machine learning models work well because of the humanly designed representations and input features. As I told you, when we need to predict whether a participant is male or female, we identified what should be the right features: hair, weight, height, or shoe size. But if this is given to the computer to identify the right features in data, probably based on certain mathematical concepts, we will get much better results. So machine learning models, this work has to be done by humans, identifying features, input features, and then we have to design the representations. Okay, so this work is done by humans. So and ML, these machine learning algorithms then just optimize the weights. As I told you, 0.4 weight I give to hair because it's more good predictor for a male female. And shoe size I will give 0.3, again a weight, because it's again a better feature than weight. Weight I gave 0.5. This is not by human. This is the algorithm will detect it from the data, but features we identify and give it to the machine. So machine learning algorithm. So what best is here is that why doesn't a machine automatically identify the right features by seeing lot of data? Okay, so so the focus here is that we should be able to describe our data with features which computers can understand, and learning algorithms normally optimize the weights. So if these two features are embedded by some other technique, probably our results will be much better. And the model which does it today is known as deep learning. Then what is machine learning and difference between machine learning and deep learning? If you see this figure, we train our machine with the input features of a car. So if you show any car to the machine learning algorithm, it will detect whether so if you show an image to the machine learning algorithm in this picture, because humans have seen that it has got four wheels, it will have two shields, it will have a bonnet. So all these things we tell the algorithm, and the algorithm, once you show once you show an image to the algorithm, to the machine, it will say that whether this image contains a car or not. But it was here the human who did the future extraction and put it in the algorithm to detect that whether it's a car or not. But in otherwise, it does not normally happen. Say, if if we use another alternative is if we use deep learning, where this human part is taken off. Human does not have to identify features. Let the algorithm itself identify features. It does the feature extraction. It does the classification. So the human part is even done by the computer. And when you give the car, the algorithm identifies the right features and the prediction and predicts whether it is a car or not a car. Okay, so a better way of doing this learning is now deep learning. So again, that is that's it's there's a lot of research going in this area of deep learning. And so a deep learning is basically again a subfield of machine learning, and the advantage is that it does representation of data by itself. It identifies the features which are more relevant. And um, and the advantage is it uses multiple layers of neural networks, a hierarchy of layers in neural networks. And if you provide lots of data, it understands it and it identifies the right features from that data. So when you have a lot of data, the better way is to use a deep learning model to have better accuracy. I hope by now we are clear that what is a AI system, uh, and what is machine learning, and what is the role of deep learning in AI systems. Okay, so if you have, there's again a graph which shows that deep learning is showing much more results, better results than mm, machine learning algorithms. So in case of machine learning, the features were overspecified, incomplete, and used to take a lot of time to design and validate. So, and it was to be manually done by humans. Learn features are easy to adapt. So because this deep learning automatically learns the more relevant features, and this is fast to learn because machine is doing it. So and it is based on some mathematical concepts where we identify the better features. And then it provides a very flexible universal learning framework for representing world visual and linguistic information. Again, these models, because the best interface with humans is natural language. In addition to it, the better way of passing an information to a computer would be visual information. And representing both these world and linguistic information represents the world scenes. So if you have to represent a world scene to a computer for making an intelligent decision, then you need to give the real features of that world scene. And that can be done with the help of a deep learning system. So it can learn from you both unsupervised and supervised algorithms. It is effective from end-to-end joint system learning. So from beginning to end, you can start learning, and it has a capability of utilizing large amount of training data. In every learning algorithm, you have training data and you have testing data. So without training, you cannot test. So you have to train the algorithm by which it will learn some weights and use that weights in then testing data. Okay. So in 2010, the more work, so actually this deep learning is based on neural networks. And neural networks was given earlier in 80s, but it got a hype back in 2010 when Hinton at University of Montreal actually worked on neural networks, and the results which he showed were much better than any machine learning model up to that stage. And now, after 2010 till date, there's huge amount of research which is being done using these deep learning models, and the accuracy with which these models do predictions or or do predictions or do analytics is very, very high. It's very close to humans. Okay, so it's again a review of machine learning. It's an area of AI that enables AI systems to improve the performance of performing a function, improving its capabilities, and enhancing its knowledge. Normally, we say a system learns only when if doing that task it had a specific performance function, and now if it does the same task and it sees that the performance function has improved, then we say that the system has learned. Okay, so Tom Michel, which is again a well-known researcher in AI, has has defined this this learning as if a task T of if a task T of a system is done with the performance measure P, and if the same task is T is done with a performance measure P plus X, which means there's some addition in the performance function, he says that the system has learned. So if there's some improvement in the performance function of doing the task earlier and doing it now, then we'll say that the machine has learned. And the type of machine learning is supervised, semi-supervised, unsupervised, or reinforcement. There are mainly supervised and unsupervised, but sometimes you have data which is annotated, or sometimes you have data which is not annotated. Then there's an advice that you go for a semi-supervised machine learning algorithm. Okay, so up to now we studied what is machine learning and what's the importance of learning of an AI system. What are the key essentials that make a AI system? Is the knowledge base, the knowledge which you have to capture from the domain, and for which you will have to take the services of the domain experts. Inferencing mechanism, rule base, which will help you to, so you take the knowledge from the humans, you convert it into a form which is understood by the machine and by the rules. So that, say for example, earlier I told you that we need to give a symbolic representation, and then you need to have a rule base or an inference engine by which you can make inferences on those knowledge to derive new knowledge. And one important thing is you need to have efficient storage and search. So all this knowledge which you store has to be searched, because there, in a specific domain you will have a lot of knowledge, and to search specific amount of knowledge you will have to do a lot of search. And for it's important that in search you actually store the knowledge efficiently, or computationally efficiently. And so search and storage are two important things. Better storage means better search. So 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 we have to store the knowledge in such a way that it is efficiently searched then. And finally, we will need certain learning strategies by which the system learns from its previous knowledge and then improves its working based on that knowledge. So these are some of the ML models which are used for learning. Naive Bayes, which is Bayesian theory for learning, and it uses probability. There's linear regression, it's another model, machine learning model. Support vector machines, again, you are very good for classification and regression. Then there are decision trees, which are rule-based again. And K nearest neighbor is an algorithm for machine learning. K means it's a clustering algorithm. Fuzzy K means it is a algorithm which is which resembles k-means, but it takes fuzzy concept into it. So for example, it uses those linguistic variables, whether it's a tall or not tall. There are certain things which certain cases which fall between two classes. So for those who use fuzzy k-means. And finally, neural networks. I was earlier telling you that Andrew Ng, who's a well-known researcher in machine learning, says that neural networks or deep learning networks, so they will be the future, and there will be one single algorithm, machine learning algorithm, that will solve most of the complex problems, and that's happening. And where deep learning uses neural networks basically. When we say layer of uh, number of layers, it is basically layers in this neural network. But there are three things when you talk of an AI system. We need to have a computational model, a proper computer architecture, and a programming language support. When we talk of computational model, a computer works on a program store concept. It was given by von Neumann, and he says that the computers can work either in a data flow or a program flow manner. When you say program flow, it means it moves from instruction to instruction. And when you say data flow, as the data becomes available, it starts making decisions. Okay, so either Now, at this stage, computer architecture has got a has got into a large amount of improvement and scalability. The this computational model, which was earlier von Neumann, now has changed to data flow, and and the in the architecture which we have today is a parallel architecture. Most of the machines which we have at home do have parallel execution units, or those machines on our kids play games. When they use GPUs, and these GPUs have multiple cores and a lot of memory also. So the computation, if you see the computer architecture support which we have today, is very enormous. So the amount of data crunching capabilities that our computers, our hardware has, is very high. Now the problem is, do we have the programming language support to utilize this hardware? And now programming languages have also improved. So to actually exploit this parallelism in hardware. So now we have got a lot of parallel hardware. We have got servers, we have got GPUs, we have got multi-core processors. So the important need of computational model is to have parallel algorithms to exploit computer architecture to actually solve the AI systems. Because as I earlier told you, the intelligence has to be extracted from data, and the data which is available today is lot of data, and we need to crunch this data and convert it into intelligence. And the processing of high amount of this data needs high amount of computational resource which are already in place. The only thing which we now need is logic and the programming support. And now programming languages are coming in today which will help us to actually use those resources. Say for example, CUDA programming, which is again a parallel processing language, sort of, for coding parallel these processors. And similarly, you have got TensorFlow, which is again which is very useful in using multi-core machines. Then there are the programming languages, they like PyTorch, which uses TensorFlow machines related to GPUs. Now we have got TensorFlow machines where we use tensor processing units. So this way we can exploit more parallel hardware which are available by using those programming languages which can actually code those machine learning or deep learning algorithms for using lot of for crunching lot of data and converting that into intelligence. Okay, so it's again that deep learning is based on neural networks, and they use many models. They have their own specified models like CNN, RNN, autoencoders, a lot of models which have improved the efficiency of AI system. And one of the key advantage of these deep learning models like CNN, RNN, and autoencoders or GANs is that they help you to identify the features which are useful. And those features, identifying those features basically reduce the complexity as well as the computational resource required for the processing. Let's see that how exactly this evolution of AI came into. So there were 5 stages. Initially, there were very naive solution stage where primitive solution to problems for humans. There was a this AI started in Texas, where there was a food processing unit. It used certain experts to actually make dried food, where you'll add water and you will get food ready by just adding warm water. So the company had a very good expert cook who used to add this material and then to the machine, and the machine would actually dry this into, and then it will be packed and sold out. Now this once this human used to, if he would stay home, this factory has to stop that day. So the owner of that company, he consulted certain computer engineers and asked them that they to give him some solution. So they started this AI system there. So they gave a solution that if he used to add 2 bags of wheat, he used to add 1 bag of sugar, or he used to add 1 bag of some masala, then then the machine would mix it and make that food for fast food. So now what they did is, they rather than they took this knowledge from the expert, and then the machine would automatically mix so much of material, and so much of ingredients, and then they will prepare the fast food. And this way, what they did is they extracted the knowledge from the chef, master chef, and then they put it inside the machine and the machine would actually use those hoppers to pop that food into the mixer. The mixer will mix and then they will produce it. This way, they converted the intelligence of the human into the machine. So this was the first stage when we had a new solution for producing AI-based system. So then it went to certain general methods. People started using the same knowledge for proving theorems or solving games. Initially, those games like chess was played using that general method. So they started extracting the game knowledge into computer, and then computer played chess with the opponent. So then it extended to domain knowledge stage, where people started using this knowledge in specific domains like medicine and in agriculture and in other fields, where they did smart farming or smart medicine, and then developed those experts based systems. Finally, this was used in multiple integration stage, where multiple fields were now integrated, and interdisciplinary AI knowledge was used to solve complex problems in multiple domains. So the same knowledge was now used in so the same methods were extended to solving problems in different domains. And finally, it went into embedded application stage, embedded various intelligent components in popular applications. Now, it is believed that 80% of the computers which we see are basically embedded computers. So you may have seen computers on desks, but you never know that there's a computer. You know it, but you never realize that there's a computer in your watch. So you never realize that there's a computer in your bike. There's a computer in your car. There's a computer in your mobile phone. So you have one computer on your desk and five computers in your pocket or in your car and in your watch and in your pen. Or females even don't know that there was a stage when they would love to wear golden jewelry, then they went to platinum, and now they will go to computational jewelry where computers will be put inside their earrings and bracelets, and clothes and footwear. All will have computers, and this will be pervasive computing and variable computing, assistive computing, whatever name you give it. The wheelchairs have computers. uh, so this stage, this is an indicative that we have more embedded computers than we have those on the desks. And these computers are not very simple computers, they are again intelligent. These computer in your watch, the watch which I have even notices the number of steps I take in a day. If I sit somewhere for more than 2 hours, it says to me, get up and have a walk. So they are intelligent. They check my working schedule. And so this is similarly a woman wearing a bracelet having a computer will be sending her medical data to a remote computer in a hospital. So if anything happens, it will notify her and ask her to come to the hospital. So she's regularly monitored for her health. So this way, uh, now these computers, embedded computers, are intelligent devices. So now it is into an embedded application stage where computers which are already there in the embedded devices will work intelligently, and they have intelligent software working on them. Is it okay up to now?
Yes, sir.
Okay, so it started in 1960s in Nave Solutions, as I told you about that food processing company. Then it went to problem solving like theorem proving or games, domain knowledge, making an expert system like a doctor, multiple integration where you integrate multiple domains together, and finally, now in a stage where it is embedded in our lot of devices. Okay, so these are some of the applications because of the areas are the roots which provide the energy to this AI tree. They involve psycholinguistics, sociolinguistics, computational linguistics, adaptive systems, cognitive psychology, philosophy of language, logic, robotics, uh, and these are all applications as well. But the main sources, the nourishment comes from linguistics, computer science, mathematics, management, electrical engineering, philosophy, and psychology. And if you see what are the fruits, they are in speech understanding, in genetic algorithms, in natural language processing, intelligent tutoring, that's education, computer vision, that's image processing, neural networks, expert systems, machine learning, game playing, fuzzy logic, robotics, and automatic programming. These are some of the applications of this AI tree. And these are the fruits of this AI tree which are being run or which are being nourished by these sciences like computer science and engineering and mathematics and management. Some of the applications of AI system is an expert system. And as I earlier told you, an expert system is basically taking the knowledge from the expert and putting it in a knowledge base and then having an inference system to extract more knowledge. So AI is a collection of concepts, ideas that are related to the development of an intelligent system. The one of the applications is expert system, a computer system that applies reasoning methodologies to knowledge in a specific domain to render advice or recommendation, much like an expert, human expert. It's very a doctor, a AI doctor, and a doctor. If I take all the knowledge from the doctor and put it into a computer system, and if it makes the recommendations just like a doctor, then it's an AI-based expert system. It is a computer system that achieves a high level of performance in task areas that for human beings require years of special education and training. So if you put it into it once, then you are free. It will work 24 by 7. Another area of AI application is natural language processing. Humans express their ideas to their fellow humans with the help of language, and they use some language which you normally say natural language like English to contact or to express their idea to the other person or to do conversations. And uh, computers and AI based systems have helped in natural language processing. Okay, and this conversation with one human and another human, internally it uses lots of mathematics, probability theory, and modeling to actually understand what that sentence means, what that say a human makes an utterance, the computer records the utterance, converts it into text, then takes the meaning out of that text. That is what comes under the head of natural language understanding. And then it processes that whatever text it has converted, and then makes creates another text answer to that question, and then makes an utterance. So it takes utterance input, processes it, and gives a utterance back. And behind this, there's a lot of data that's processed, and there are a lot of problems that it must have solved. Say, for example, a user says an ambiguous sentence to the machine. The machine has to first remove the ambiguity. If there is some noise, it has to remove the noise, and it has to correct the sentence, convert it into a right meaning, and then understand it, and then reply back to the user, which is again all behind is done NLP and then text synthesis. One of the good example of NLP is recommendation system. One more application of AI is speech understanding. It text translation of human voice into individual words and sentences understandable by a computer. So what it exactly means is, mm, we normally have inquiry assistants in hospitals or in airports or railway stations. You have an inquiry counter, you have to go there, the human, you have to put an inquiry to him, and the human understands, and then he replies back. These are being replaced by computers. You'll go to the inquiry counter, but you will not know that whether there's a computer inside or whether there's a human inside. You will make a inquiry. Say, for example, you will ask that what is the next flight to Delhi. The AI system inside will take your utterance, then it will search its database for the next flights, and it will even tell you any hopping flight between Srinagar to Delhi. And this all will be based on lot of process data, and then it will even reply back in the same audio utterance as you did. and you will not come to know that inside whether it was a machine or whether it was a human. So these such systems are known as spoken dialogue systems. So you make a dialogue with a machine, and all conversation is being done in voice based manner. So you put a reply, you put a query, and it gives a response. You can give a query, you can give a response. If an other person on the right hand side, on your side, gives puts a query, it will reply to him also. So these systems are multimodal systems which take an utterance in, process those utterance, and then respond to you. And such systems are known as spoken dialogue systems. That's one more application of AI. So that will actually balance the barrier between the humans and the machines, where humans normally use natural language for interface, and these machines will also now, they have already worked, there's a lot of work having done in this area, and they are doing the, and there are a lot of conversation agents basically being used abroad, in applications like these inquiry counters, or as technology assistants, or in educational assistants. Okay, one more application of AI is robotics and sensory systems. The vision systems, tactical system, and signal processing systems are some of the applications. So, grading of apples based on images, or based on video of an apple, and grading it into class A, B, C will be one such vision system that can be created, that is already created for grading apples or grading any type of fruit into different classes, is already in place. So that's one way of saying sensory system. Then we have got robots, or applications of AI. They have the capability of performing manual function without human intervention. An intelligent robot has some kind of sensory apparatus, such as camera, that collects information about the robot's operation, its environment, so as to interpret and respond to any change, and rather than follow any instruction. So it does it automatically. It sees, it scans the room, it checks the walls, it moves according to the hindrances, and it avoids hindrances. And if it is given any task, it will do it. Be it carrying goods from one place to another, it will be done. Amazon uses robots for its all warehousing functions. So that can indicate that how these AI based robots are actually doing things and are used in practice. One important application of AI is in computer vision and scene recognition. Uh, when we say computer vision, it means uh, basically uh, anywhere we use visual information, such as cameras, and for example, self-driving cars is an example of computer vision, where we make use of cameras to actually interpret the scene and accordingly control the different parts of our car to move on the road. So this is already such cars have already been in on roads in US, and there may be some mistakes by such machines, but normally they have been seen that they are already in place, and there have been minor accidents. Otherwise, they have been successful. And this self-driving cars is an example which has been used by US military in 1990. The research has already been done very before 30 years. Now, from last 5 years, they have come into industry, manufacturing industry, and now manufacturers are using those cars. Okay, so the addition of some form of computer intelligence and decision making to digitize visual information received from machine sensors such as cameras. So it actually understands. Self-driving cars is a good example of visual recognition, and the basic objective of computer vision is to interpret scenarios rather than generate pictures. So this US military has used this maybe this computer vision and AI during their wars. In this has remained successful in this desert storm with Iraq. They used a lot of computer vision and image processing actually to attack the Iraqi bases. By sending their aircrafts, pilotless aircrafts, which we now call as drones. They would fly their drones over Iraq, and these drones would then take the images of the area, immediately sent to the Pentagon, where the huge supercomputers will process those images and identify the Iraqi bases and then attack. And this AI and this computer vision and image processing has had a more uh, success during this Iraqi war. Okay, so computer, one more application of AI is in education. So intelligent computer aided instruction. The use of AI techniques for training and teaching with a computer. This intelligent tutoring system can help guide learners in how best to proceed with learning process. So here on the educational process. So there are a lot of online teaching happening, and lot of these companies who provide online teaching say that they use AI technology underneath. They say that our systems are based on AI. Our systems monitor the students and then suggest that how they should improve the and what area they are weak and what area they are strong. They will monitor their uh, performances and accordingly schedule their classes. Okay, so one such technology was engaged. This AI based technique was taken by government of India in a project which is known by the name of computational education, and it was to be developed by Microsoft, and the project was given by NCERT to this Microsoft, where when we talk of computational education, it basically means uh, uh, there will be some text, there will be some video, and there will be some animation. If a student is studying second laws of motion or motion laws of motion, and if he thinks about Newton, probably when we say third law of motion, we say this Newton was under an apple tree and he saw an apple falling down and he said there was gravity and all these things. He's then the immediately the concept which a student may have is that he wanted to see the apple tree where then this Newton was sitting. So this computational education says that whatever comes to the mind of the child should actually be available with whatever sources the model uses. Say, for example, there are internet videos or there are animations or whatever sources there are or means we can imbibe that concept. It should be available to the student based on that on that topic. And or somebody is into games and he is playing game or he is watching cricket and he sees a player, let's say Sachin Tendulkar. He is more interested in knowing his lifestyle, his personal life, and so there should be information about everything, and it should be computationally. So anybody who is interested in any area should be available. So this way he will get more interested and learn more and remember for long. So that is how this concept will help in lifelong learning. So computational education is a big project which is happening throughout world. People are working on it, thinking of uh, how to engage learners using these computational techniques. For computer science people, the big problem is programming. Now, a lot of work is being happening in this area where automatic computer programs will be generated, uh, and so AI techniques will be embedded in compilers where they will aid the programmers to program as humans do automatic programming. Now, maybe in future, computers will do programming based on ontologies, which convert the client requirement into code as well as design diagrams. So I know one of my friend who works on converting natural language sentences from the client, because the client, in case of software design, we hear the requirements from the clients, and then we have to convert those requirements into diagrams and the software diagrams, design diagrams, and then send these design diagrams for coding. So my friend who is in Germany works on this. He takes natural language sentences input from the clients, and his software converts the design diagrams and even gives the skeleton code. Okay, so it's a sort of semi-auto programming. So a lot of work of programming or development, software development, is being done by his software. He takes the NLP sentences, identifies what should be the objects, classes, and all functions, and he then his software designs that. So internally, I have had a chat with him, and he says that his system uses ontologies. One more thing about AI AI is incomplete without neural computing because it resembles human brain. A neural network is basically a collection of neurons connected, having certain weights on their links, and it resembles human biological neurons. In human, these biological neurons get activated when it receives a signal. Similarly, computational neurons get activated when they receive data. Okay, so uh, it resembles human. An experimental computer design aimed at building intelligent computers that operate in a manner model on the function of the human brain. So this neural network is basically a replica or of a human brain in computational manner. It's artificial neurons. One more application of AI is in game playing. This was one of the first areas that AI researchers studied. After that naive stage, this was the stage when people actually tried to use rules for chess rules for playing chess. At that time, the game playing became more concentrated, and people thought of using AI in games. So it was a perfect area for investigating new strategies and heuristics because the results are easy to measure. Yes, so even the well-known chess players were beat by this uh, by the by the Google's DeepMind. Another important application of AI is in language translation. Language translation means in from one language to another language. Say, for example, we have to convert Kashmiri into Arabic and Arabic into Kashmiri, its translation, and machine translation or language translation. We use computers to translate from one language to another language. So automatic translation use computer programs to translate words and sentences from one language to another without much interpretation by humans. These these machine translation or statistical translation or grammatical translation, where we use grammars or statistics to do translation of one language to another language so that the meaning does not change in sentences, uh, and the grammar is also maintained, uh, is again a big challenge even for humans. But computers have had success to a certain extent by involving this AI, by involving the knowledge of the language, uh, by involving the vocabulary of the knowledge, and then having mapping between rules of the knowledge, and then seeing lot of text of a particular knowledge, which is learning from corpus. And this way, machine translation or language translation has been the AI has actually helped in this area, in translating from one language to another language. There's a project which is going in European Union by the name of Molto, and this project has given a framework which converts, which does language translation between around 32 languages, which include Arabic, Urdu, Hindi, Sanskrit, some Nepalese and German, Finnish, English, all those major languages of the world, Chinese, Japanese, the main languages of the world, and uh, and it has been successfully doing it. Even Google uses that framework for its translation purposes. Because one of the main challenging problem in AI uh, is fuzzy logic. The fuzzy logic is about problems where sometimes it becomes complex to identify. Say, for example, we say a person, any person who is more than 5.9 is tall. Now, this 5.9 is tall, it's okay. Somebody is 5.9, we can call him tall. Somebody is 6, we can call him tall. But if somebody is 5.89, what would you call him? Would you call him short or would you call him tall? So this is a very fine ridge where we have to make decisions. So such decisions where we cannot directly decide between 0 and 1 is known as fuzzy, and this fuzzy concept has to be dealt with to see with to which what it belongs more. In that case, we use again a theory called fuzzy theory, a fuzzy set theory. So we see the membership of a particular value to a particular item to which class. So if if it has more membership to the tall class, so we'll say it is tall. Then 5.89 will have more membership to the tall class rather than short class. So we cannot say 5.89 is short, rather we'll say even it is tall. Okay, so uh, this fuzzy logic actually solves very complex problems, especially in weather forecasting and in text processing. So it's a technique for processing linguistic terms, as I told you, short and long, tangible, intangible. All these things are very complex when it comes to deciding. Logically consistent ways of reasoning that can cope with uncertain or partial information. It's characteristics of human thinking and many expert systems. So this most of the machines use this fuzzy logic. So that means they can decide. They have the capability of deciding even between fine lines. Okay, and between dirty and not dirty, but it can even identify the range between dirty and not dirty. So there's a fuzzy logic washing machine which says the machine people say that this machine uses fuzzy logic. So that means it is using AI, and the AI is based on very fine line. So even if you are it will not, even if you are no, there will be a fine difference between dirty and not dirty. It will even work on that fine lines. Okay, genetic algorithms. Genetic algorithms basically based on evolutionary algorithms, and evolutionary algorithms again is the same from medical concept, saying that there are chromosomes which mutate and then they have a population. Out of that population, some live and some die. Those live, they again mutate, and they have different type of chromosomes, they have different type of genes, and then using the same genetic, that is what is genetic algorithm. And these genetic algorithms have given search algorithms or search techniques, strategies to solving very tough problems of real world. So they have their own application. Now we'll go to what exactly is meant by an intelligent agent. Expert or a knowledge-based system embedded in a computer-based information system to make things smarter. Okay, so any intelligent agent is one software system which can use knowledge and and then make certain informative decisions so that they actually work in a smarter way. So these AI-based, these intelligent agents, what they will do is they will sense their environment. Okay, so for sensing, they use sensors or cameras. They sense any. They will be watching their environment, and then they will use their internal knowledge to decide that how to react to that, what they take as input from the environment. And once they react, uh, they may have to change certain knowledge which they have. So a simple AI agent is simply a software system which actually checks the environment, senses the environment, checks the knowledge base, and then reacts to that change in environment. And this way they become more smarter. So now, after this applications, our this next objective is to tell you how to plan a AI-based system. And here, when we talk of AI-based system, because the participants come from different areas, so we'll just tell you an expert system, because also we are going short of time, so I'll have to skip some slides and focus on more important few slides which are at the end. But I'll just go through these slides a little faster. And so I have already told you what's an expert system. Expert system are computer-based information system that uses expert knowledge, so which comes from some expert of a particular domain to attain high-level decision performance in a narrow problem domain. So we normally take experts, they extract some knowledge from them, and then represent that knowledge in a system and add inference rules, and then make conclusions from that knowledge. So the basic concepts of expert system include how to determine who experts are, how experts can be transferred from expertise can be transferred from a person to a computer, and then how the system works. So the first objective is to identify an expert. So, take the knowledge from the expert and dump it into a computer. Expert is a person who has special knowledge, judgment, experience, and methods to give advice and solve problems, along with the ability to apply these talents. A decision performance and the level of knowledge a person has are typically criterion used to determine whether a person is an expert. So you have to identify who is a domain expert. And what do you may mean by expertise? The extensive task-specific knowledge that experts possess. A level of expertise determine the performance of a decision. Training, reading, experience in practice achieve expertise. These are some of the features of an expert system. One is it should be have an expertise, an EX. An expert system must process expertise that enables it to run on expert level decision. We should have the symbolic reasoning. Knowledge must be represented symbolically. I will tell later how we represent it symbolically. Should have deep knowledge, concern the level of expertise in the knowledge base. Self-knowledge must have a strong learning capability and update their knowledge constantly from success, failure, and other knowledge resources. Why we need these expert systems? Since experts may retire or leave, because as I earlier told you about that food company, if the expert chef would remain absent, the company would not work that day. Experts, so if they retire or leave, expert systems are an excellent tool for preserving professional knowledge crucial to a company's competitiveness. Expert system is an excellent tool for documenting professional knowledge for examination and improvement. Expert systems are good tools for training new employees and disseminating knowledge in an organization. They can also allow knowledge to be transferred more easily at a lower cost. So these are some of the expert systems which are already in place. One is Dendril, which is useful for molecular structure identification. So it's an expert system. Given the features, you can identify the molecular structure. Mycin for medical diagnosis. XCon for configuration of the VEX computer. These are rule-based system where a system in which knowledge is represented completely in terms of rules. When we say rules are you have to give an if condition and a then condition. The part which we write in the if condition is known as antecedent, and the conclusion which comes after those if conditions is known as uh, consequent. So we say the system based on production rules. So these production rules are like, if this is the temperature, then the patient has malaria. So this then becomes the consequent and it becomes the antecedent. So the applications of these expert systems are in credit analysis system, in checking the credibility of a client, used in banks for risk management assessment when they give loans to clients. Pension fund advisors, it will help employees to plan their retirement through their analysis that can calculate their pension benefits under different scenarios. Automated help desks enables some small businesses to deal with customer requests more efficiently. Security systems, okay, for surveillance, market surveillance systems, business process re-engineering systems. So all those businesses where they need to change their processes, or business reprocess engineering. So they re-engineer or they change their processes in identification the faulty parts or faulty subparts, and replace them by efficient parts. These are some of the areas where we can apply our expert system. Once finance, data processing, marketing, human resource, manufacturing, homeland security, business process automation, and healthcare management. All these are the area where expert systems can be applied. So these are the structure of an ES system. You need to have a development environment, parts of an expert system that are used by builders to build the components and put knowledge in the knowledge base. Okay, I'll skip some of the slides just to take you to a place where, because we are left out with lesser time now, we've got 20 minutes, and I'll just take you to, okay. These are the, if you have to build up your own expert system, these are some of the things which you will have to concentrate. One is that you need to have a knowledge base which you will extract from the experts. The knowledge which they have, you'll have to extract that and then represent them symbolically in a form that you can build up your knowledge base. Then you need to have an inference engine. Inference engine is a set of rules by which you can extract more knowledge from the already existing knowledge which you have taken from the expert. And a user interface where a user can interact with your system, okay, and so that he can actually derive more knowledge, and he can actually ask a question to the system and the system gives an answer. It can also have a subsystem which is known as knowledge acquisition subsystem, where from we can keep on adding more knowledge. Blackboard workplace, where it's a memory where the knowledge rules and facts are brought in. explanation subsystem justifier. Sometimes people need to, so if let's say that if we say that if the temperature is high, the person has a malaria, so some justification, it's not it may not be very simple, it may involve many rules, so we need to have to justify that why exactly we decided that he has got a malaria. So maybe he may have done some blood tests or some other medical tests, pathological tests, based on which based on which the expert system uh, decided that the patient has got a malaria. So it has to justify that his temperature was this, should have been this. So all that justification can be done given by an explanation subsystem or a knowledge refining system. Sometimes with more experience and with more learning, the knowledge in the system has to be changed, because over the time things change, and this change has to be replicated. It has to be brought in the expert system. Knowledge acquisition has to be extracting and formulation of knowledge derived from various sources, especially human experts. So getting that knowledge and putting that in a form that it can be used by the system is known as acquisition. Then building up that knowledge, a collection of facts, rules, procedures organized in schemas. So that's a knowledge base. You have an inference engine, a part of an expert system that provides a methodology for reasoning about information in knowledge base on blackboard for formulating conclusions. So this is the inference rule. Inference engine is basically a system which comprises of inference rules. And some of these rules are like modus ponens, modus tollens, hypothetical syllogism, conjunction, disjunction, or all these are certain rules.
Karo, bu şey ya diye.
Okay, so they use those inference rules to derive more knowledge. And user interface for users who can actually put their query and they get the result. The part of the computer system that interacts with the users, accepting commands from the computer keyboard, displaying the results generated by other parts of this expert system. And then you have a blackboard, which is an area of memory aside for description on current problem and for recording immediate results in an expert system. Then you have got an explanation subsystem which explains the system's reasoning and justifies its conclusions. A knowledge refining system is a system that has the ability to organize, analyze its own performance, learn and improve itself by for future consultation. So I'll just skip some of this again because we're left with less time. Okay, so one important thing that we should know is if tomorrow you plan your own expert system in your own field, you may have the enough knowledge. So you will be advised to convert your knowledge into English sentences. Say for example, here the English sentence is the tall woman is 23 years old. So similarly, you may have some knowledge about your own domain. And where you are an expert, so you will convert it into an English natural language sentence. And then there are tools. Say for example, there's a language tool called OPS5. This will help you to convert it into a symbolic representation which is written on the right hand side. The OPS5 will take this English sentence and convert it into a form which is known as symbolic representation. So it writes woman arrow height tall arrow age 23, which says woman and height tail and age 23. So this is the fact. This sentence has been converted into a form which will now be used by any inference engine. Okay, then there's another sentence, the job entry system queue space is critically low. So it will say job entry system JESQ mode panics. So that means if the space is critically low, you need to go into panic. So this is known as a knowledge engineering language. So knowledge engineering language is a sophisticated tool for developing expert systems. So whatever English sentences you have about your domain have to be converted into a symbolic representation using a knowledge engineering language like OPS5. Okay, so it consists of an expert system building language integrated into an extensive support environment. Then this language, which it converts it into, will be used by other expert systems, which I'll show you later. And then that can be used for making more inferences or based on the knowledge which you give. A programming language is an artificial language development to acquire knowledge, accept, reject knowledge to control and direct the operation of the computer. So because your expert systems accept knowledge in symbolic form, so it will we advise that you convert, because some of you may not be expert in computer science. So those who are in computer science can use any programming language for that matter. But for those persons who are not computer engineers or experts, So what they can do is they can give natural language sentences to these OPS5 tools, and that will convert it into this language OPS5. And this OPS5 then can be given to any skeleton or knowledge engineering system, which will convert that, which will add some rules and help you to do inferencing. I'll show that again in another slide. A skeleton knowledge engineering language is simply a stripped down expert system that is an expert system without its domain specific knowledge removed shell. Normally, if you see this picture here, this is a Mycin, a medical diagnosis, disease diagnosis system, but it has got three things. One is the support facility, a knowledge base, and infection disease expertise. So this knowledge base contains expertise about infectious disease. So the expert who has developed this Mycin had lot of knowledge about diseases. So if you give some symptoms, it will identify the diseases. So but what people did is they converted into a skeleton based system. So they removed this infection disease expertise and kept it empty in the right hand side. The rest inference engine was same, the rules were same, the support facility were same, but the knowledge base got empty because this way it would work only for infectious disease. Now if you add your own knowledge into this knowledge base, which is now e-mycin, so it will work on your knowledge. So only thing is, first you need to convert your whatever knowledge you have acquired from your domain, convert it into OS5 uh, language, symbolic representation, add that to e-mycin, and your e-mycin will start working as an expert system in your field. Okay, so similarly, there are some examples. The designers of Prospector stripped it of knowledge. So there's a tool, expert system, which works on geology, and they converted the same Prospector for diagnosis and classification of diseases. Okay, so they simply they changed its knowledge base, rest inference engine, and support facility remained same. Then Mycin system, which was meant for diagnosing and treating bacterial infections, became skeleton system called e-mycin. Now you can add any other uh, knowledge from your field and it will work on it. Then there's another system called CASNet consultation system for glaucoma became the skeleton system for expert the field in microbiology. Okay, so these microbiological diseases. So they changed the application of a particular expert system by just changing the knowledge base and keeping the system same. You can do similar things with your with any expert system. You can identify any expert. So here, if you see this e-mycin, now these are the different applications of e-mycin. By adding the knowledge from your field, it will start working on your problem. So for example, SACON helps determine strategies for solving structural analysis problems. This is again, when you say structural analysis, civil engineering. Blue box helps select therapy for hospital patients with depression. PUF diagnoses lung disease by interpreting laboratory pulmonary function tests. LITHO helps characterize underground rock by interpreting oil well log data. This is geology. Plant, it goes into whether or not cornfields will be damaged by black cutworms. So this is how you change application of e-mycin. It was actually mycin. Now in Mycin, you remove the knowledge base. Now, if you add knowledge bases of corn crops, it becomes plant DCP, CDP. If you add about geology, it becomes litho. If you add about pulmonary diseases, it becomes puff. If you add about patients with depression, it becomes blue box. And if you add about structural analysis, then knowledge about structural analysis, it becomes SACON. This is how you change the functionality of an expert system by just converting your knowledge into OS5, which is a symbolic representation language. There's one more knowledge engineering language known as ROIS, and again it is you can convert your natural language sentence into ROIS, and then it can change its application based on being in whether you use, in this case they have used it for Air Force, they have used it for battlefields, for construction claims, and for chemicals and product liability cases. So the application changes by changing the knowledge base of our expert system. So with this, I stop it here. If you have any questions, you can ask me now.
Well, thank you very much, Dr. Manzoor Chachu Saab. It was really a very exhaustive presentation, you gave a detailed account of all aspects related to artificial intelligence, its evolution, its applications. Each and every aspect has been covered very well. And I'm sure there would be hardly any doubt that would have been left with the participants would have been left with. But still, if anybody has a question, I will just unmute all the participants. And if any participant has any question, please feel free to ask. Just a
Yes, sir. May I ask a question?
Yes, so please go ahead.
minute. First,
Manju, sir.
and yeah, please. Then Muzaffar Hussain Najjar, please conduct the question answer session. Our moderator of
Okay.
Okay, sir. Okay.
Manju, sir. Thank you a lot for this nice presentation. The Lord just want to have a query regarding this one of your slides where you showed like where, for example, when we log in into our bank accounts or something to identify us from that we are not a machine, we are a human being. They put this visual deformed text. How long do you think it is going to work before the machines cannot even recognize this? Number one, this was question number one. Question number two, and how much should we be afraid of, like where the AI will take it? I remember 2 years back or 1 year back, there was a photograph of this, the CEO of Facebook having his camera of the laptop blocked. If a person like him is so afraid of this, how much we should be?
Basically, this is an evolving area. And there was one time in one of my talk, one asked me that, sir, you are making robots and they are intelligent. Are they not going to be a risk to human life? Say, for example, robots take over and they become a risk to human life. They will kill us. The answer is that it looks very fancy when you see movies and you see robots killing humans. It will take decades to go to that stage, what you see in movies. It's virtually okay, but still AI is in infancy. It's not, it may have evolved, it has been used with purpose to make life easy. These AI systems have never been designed with an intent to actually create problems for human life. But yes, in certain stages, when machines fail, they can become danger. That's quite obvious. So if it is if there happens a small failure in some, I'll give an example. One patient in UK died. He was under critical care and he was given to an AI-based system. His pulse, his blood pressure was monitored and his glucose levels were controlled by a computer. There was some error in a computer program and the machine pumped more glucose in his body and the patient died. So you can say that way, such AI-based system can be dangerous for human life, because sometimes you have to trust the machine when actually when you want 24/7 monitoring, probably you will have to give it to computers and computer run devices like these AI-based systems. So some amount of risk has to be taken. So there's a big saying that big wins need big risks also. So if you want, so this there will be a small amount of risk, but this sometimes is not intentional. Okay. So regarding that question about those CAPTCHA tests, yes, computers over the time will evolve and try to analyze what text you are writing, and they will more accurately even fill the text. So, but that such things are being done by malicious people with an intent to destroy the databases of their competitors. So normal ethical programmers, they do not do such type of work. Okay, so the computers will even, the way image processing is evolving, and the quality of research that's happening in image processing, these CAPTCHA tests will come over. Now what they have done is they have now started giving images of mountains, and they'll give you 10 images, and then they will say that identify the footpath in those images. So that becomes a little complex for the computer to understand. They will understand the image, they will even identify the footpaths, but they have to select the images where the computer fails. So sometimes they say that press the button. The computer cannot press, it can type, it can send a voice signal, but it cannot press a button on your screen. So there it fails. So the tests are made more and more complex, so that if AI-based system moves one step ahead, the people who design the test, they also think in those lines.
Excellent. Thank you, Manju sir. Thank you a lot.
Any other question?
Yes, sir. Hello.
Yeah,
Yes,
go ahead.
Yeah, sir. My question is, sir, of all the competitive speech understanding systems today that we use,
Mm-hmm.
they use, sir, hidden Markov models. Sir, while trainable, these systems have some, sir, unfortunate properties. They have much higher, sir, error rates than we might desire. Sir, they require some restrictions in domain, and they are often, sir, inordinately sensitive to the choice of microphone. Sir, I doubt, it seems doubtful rather, that people use hidden Markov models internally. Sir, my
Mm-hmm.
question is, can we build an AI speech understanding system that is based on a very different principle?
See, first of all, when you say hidden Markov models, basically whenever there's noise, hidden Markov models use probability theory in such a way that any word that is missed in a text based on a language model is compensated with the right word from a corpus which have for on which the machine has been trained. So what we do is, say, for example, if I say that I am moving dash the bank, so this machine sometimes does not understand whatever the reason, maybe the reason of microphone, so it misses the word to. Now this two has to be filled by the computer. The beauty of the hidden Markov model is that it will understand, or it will, based on the corpus or based on the body of the text on which it has been, which it has seen, using the probability of two and other words, it will rightly identify the word two and fill it and help you to understand. Even though when you actually started taking this utterance as an input, you might have missed this word too. But with this model, hidden Markov's model, the advantage is that it will be filled up this missing value, missing word, and you will have a complete sentence. Now, this model can then use any language model internally. So it can be a trigram, a bigram, or an n-gram. Okay, so this way, that's why normally people use hidden Markov models. But there are other models also which people are using, like partially ordered hidden Markov models, or it's called PODMP. And similarly, there are other models like CLOV. Now people are using CLOV, and statistical models like WordVec and other hidden model, these skipgram models. So there are a lot of models. The earlier model which people were using even before MDPs or Markov decision processes was hidden vector support model. So people are using them depending upon the type of application and the type of need. So these are all for the aid of researchers. So they can use any one of them depending upon the application. But hidden Markov model has seen very important application, especially when it comes to noise and outliers. The two big problems in research in computer science, especially with AI, is if you have noise and if you have an outlier. A lot of research in terms of optimization is also done on the same area.
Okay,
Hope I
sir.
answered your question.
Yeah, sir. My second question was, sir, how do we make, sir, green artificial intelligence systems more energy efficient?
Say green, or when you say green, this green computing basically is a big
So green
area.
AI systems.
Yeah. No, so let me first tell you, green computing. Green computing, and when you say the type of waste you generate, which is because of computing, whether it is computers or whether it is the different parts of a computer which actually create this waste. So when you say green AI, it is basically how you use artificial intelligence in a way that we do not generate waste. Okay, so this is still a area coming up. It's a new area of research, and it will involve lot of basis on both at hardware and on software fronts. Okay, so it's still a new area of research.
So my question was how to make it energy efficient.
See, energy efficient is you might have see. I actually specialize in an area called parallel algorithms for AI systems. Using parallel algorithms means using multi-core machines. When you use multi-core machines, the amount of energy the major power that is used in a computer is a processor. When you embed multiple cores in a processor, you see this. I don't. You must have seen, because if you, by the words you speak, you look to be a computer scientist, and if you see that the energy which is dissipated in a computer is only the processor. If you take out the fan, the computer processor is like a red hot chip. Okay, it goes so hot. So energy wise, it consumes a lot of electrical energy, and it generates a lot of heat. Now what happens is, if you want this energy efficient AI based system, so you'll have to switch over to the parallel processors like the GPUs or like multi-core machines now, which have got TPUs or GPUs. So this way they consume less power because they share a lot of internal resources, whether it is memory or whether it is the processing elements, and you get more results in less time. In addition to it, first the power consumed is less, and the heat dissipated will be also less. So the heat is directly proportional to the amount of energy consumed by the processor. So that is why people are switching over to TPUs and GPUs. One server costs around 2 crores rupees of a TPU, and if you want to buy a GPU server, it costs 2 lakhs, because they are energy efficient servers, energy efficient processors. That way they both consume less power or they generate less heat. That's how you talk of green computing. So in terms of hardware, you have this, and in terms of algorithms also, you have to devise those mini batch algorithms or parallel algorithms, and use those parallel algorithmic designs for such machines, for giving for actually making them energy efficient. I hope this again is clear to you.
Thank you,
Any
sir.
any device any device which consumes less power is an energy efficient device, and any device which generates less heat is again a energy efficient device. So to do that, you will have to switch over ultimately to GPUs and TPUs.
Thank you, sir. I appreciate your effort.
Dr. Muzaffar Saab, please conclude now.
Okay, sir. Okay, sir. Sir, Dr. Manzoor Saab has discussed this important and modern concept of this artificial intelligence in detail, and he has thrown light on many aspects of this artificial intelligence technology. So I, on behalf of participants and HRDC Center, University of Kashmir, I thank Dr. Manzoor Sahab for enlightening us about this important technology. Thank you, sir.
Thank you very much. And with that, we come to the end of this session. So we are left with no time for the participant presentations. Therefore, the participants who were supposed to present in this session will now present tomorrow, because it's already 4 p.m. So we will call off at this point of time. And today's presentations will be presented tomorrow by the participants. This time we will end the meeting. Thank you very much to all of you for your patient listening. Inshallah, tomorrow we'll, if everything else permits, the weather and all, so we'll meet at 10:30 tomorrow. Tomorrow also we'll meet at 10:30 and we'll continue with the participant presentation first, followed by the lead lecture. Thanks a lot. Bye for now.
Thank you, sir.